Have you ever stared at a math problem that just looked completely, utterly impossible, like a riddle with no answer? Well, today we're diving headfirst into one of those. And trust me, by the time we're done, we're going to crack it wide open. So, meet our villain for today, a monstrous 15th degree polynomial. I mean, just look at that thing. With all those giant numbers and terms stretching on and on, trying to find the exact value for x feels like a fool's errand. This is the kind of equation that can make even powerful computers sweat. And that really leads us to the core mystery here. Is it possible that buried inside all of that mess, there's an answer that's actually simple? Or are we stuck with just getting kind of close to the real solution? That is the big question we're going to tackle. But before we can find that beautifully simple solution, we gotta talk about why the old school methods, the ones mathematicians have used for ages, just fall flat when they come up against a beast like this one. Here's a good way to think about it. The traditional methods on the left, they're kind of like taking a blurry photo of the answer. Yeah, you can make out the general shape, but all the important details are lost to tiny rounding errors. But a symbolic solution on the right, that's a crystal clear 4K picture. It's the exact value, perfect, down to the last detail. And that's really the heart of the problem. When you have an equation this big, those little approximation errors start to add up, they snowball, and pretty soon your final answer is way off. It's just not reliable. We need a different tool for the job. And that brings us to the hero of our story, a totally different way of thinking about the problem called Ezouidi's theorem. So, what is this theorem, really? Well, you can think of it like a master key. Instead of just guessing and checking and getting close, it follows a very clever step-by-step process to find the exact symbolic roots. It's designed to solve the very problems that old-school algebra just gave up on. All right, so now we get to see this theorem in action. And don't you worry, we are not about to get bogged down in a bunch of terrifying formulas. We're just going to focus on the results, which honestly are pretty mind-blowing. Okay, so the first step is to reframe our polynomial a little bit. See these S terms? Instead of the big numbers, we have these symbols. Think of them as placeholders or secret ingredients. The whole point of the theorem is to figure out the exact value of every single one of these, from S0 all the way to S14. And the way it finds them is recursive. Now, that sounds fancy, but all it really means is that each step builds on the one before it. You find the first answer, S0, then you use that result to help find the next one, S1, and so on and so on. It's like a chain reaction of logic. So after all that, what does the theorem's complex calculation spit out for that very first symbolic coefficient, S0? The answer is 0. A nice, simple, clean 0. Okay, interesting. But this is where things start to get a little weird. What about the next one, S1? The theorem calculates that, and guess what? It's also 0. And the next one after that, stick 2, you guessed it, 0 again. You see the pattern here? This isn't just a coincidence. The theorem is uncovering something deep and simple, hidden inside the complexity. And this pattern just keeps going. One after another, the process reveals that every single one of these symbolic coefficients is exactly, precisely 0. The whole thing, from start to finish, all those complicated building blocks were nothing all along. So now we get to the big payoff, the final aha moment. What on earth happens when we take this incredible result and plug it back into our equation? So remember this setup? Our entire polynomial was built on these S coefficients that we just spent all this time finding. What happens to the equation when every single one of them is actually 0? Well, every one of those complicated terms just disappears. 0 times x to the 14th, that's 0. 0 times x to the 13th, also 0. All the way down the line, the complexity just gets wiped out. It all just vanishes. And this is what we're left with. Our terrifying monster polynomial was just a mask for this stunningly simple little equation, x to the power of 15 equals 0. I mean, the difference is just amazing. And the solution from here is, well, it's obvious, right? X has to be 0. The fancy term multiplicity 15 is just the formal way of saying that because the original equation was to the 15th power, we count that root of 0 15 times. an unbelievably elegant answer that was hiding there the whole time. And this really brings it all home. The reason we can be so confident in this answer is because every single step was purely symbolic. There was no rounding, no estimating. This means we know for a fact that x equals 0 is the one perfect. Error-free solution. No blurry photos, just the truth. You know, going through this whole process really makes you wonder, doesn't it? It proves that sometimes the most intimidating, complicated-looking problems out there are
Not talking about the kind hiding under your bed or in a closet.
Hey, not that kind of monster.
No. I'm talking about a mathematical beast. Something that, if you saw it written out on a sheet of paper, would look absolutely terrifying.
You are definitely starting us off with some drama today.
I always try to. But seriously, picture this. You have an equation.
Yeah.
Usually, we deal with nice, safe things like x squared plus something. Or maybe.
Maybe x cubed if you're feeling adventurous.
Right. But this one, it starts with x to the power of 15.
That is a legitimately high-degree polynomial. Usually mathematicians see a 15 in the exponent and start looking for the nearest exit.
Right. And it's not just x to the 15 sitting there alone. It's x to the 14, x to the 13, all the way down the line. And the numbers attached to these x's, the coefficients, are massive.
Huge.
We're talking numbers like 3003, 5005, 6435. It just looks like a chaotic string of nonsense.
It certainly looks like chaos to the untrained eye, but as we're going to find out today, it's actually a very specifically ordered kind of chaos. It's a structure disguised as a mess.
Exactly. So today on the deep dive, we are tackling this specific monster equation. We're pulling from a document titled Example 15.2.
And we're not just looking at it.
No, we are going to watch it get dismantled. We're looking at a method based on Murad Sultan Ezouidi's theorem. And the claim here is, well, it's pretty bold. It says it can solve this terrifying 15th degree equation exactly.
And exactly is the key word there. That is the word that should make everyone's ears perk up.
Because usually you can't do that, right? If I hand you a degree 15 polynomial, you can't just snap your fingers and get an exact answer.
Well, usually we hit a massive wall. In traditional mathematics, you have something called Abel's theorem.
Okay.
Without getting too deep into the history, Niels Henrik Abel essentially proved that for polynomials of degree 5 or higher, there is no general magic formula. You know the quadratic formula everyone learns in school.
Oh, yeah. Negative b plus or minus the square root.
Yeah.
It's burned into my brain.
Exactly. Abel proved that no such formula exists for degree 5, let alone degree 15. You generally can't solve them using standard radicals, square roots or cube roots.
So it's considered unsolvable in that way.
In that specific classical way, yes. So Abel puts up a giant stop sign. He says, turn back, you can't go this way.
So what do we normally do when we face a monster like this?
We compromise. We use numerical methods. The most famous one is probably Newton's method. We guess a number, and then we use calculus to refine the guess, and we get closer and closer.
But we never actually get there.
Not with 100% precision. You get an approximation. You might get negative 0.999999.
Which is close.
It's very close, but it's not the exact answer. And the source material we're looking at today points out a critical flaw in that approach. These numerical methods are error-prone. You get rounding errors.
And I imagine when you're dealing with exponents like 15, small errors matter a lot.
They matter immensely. Think about it. If your guess is off by a billionth of a decimal point, tiny, right? But then you raise that number to the 15th power, that tiny error just snowballs.
It becomes a massive mistake.
A massive mistake by the time you finish the calculation.
So that's the conflict. We have a monster equation. The old tools, Newton and Abel, either say you can't do it perfectly, or here's a decent guess, hope it works.
But today's source material, this Ezouidi's theorem, says, no, I'm not guessing. I'm going to give you the exact symbolic root.
It promises to bypass the approximation entirely.
It treats the equation not as a guessing game, but as a structured puzzle that can be solved with a very specific recursive machine.
I love that image, a recursive machine. So let's look at the raw materials we're feeding into this machine. Let's break down the polynomial itself.
Right, let's look at the data provided in example 15.2. We have a polynomial p of x. As you mentioned, it starts with x to the 15.
And then we have these coefficients. The text lists them using the notation L sub nq. Let's just read a few to give you a sense of the scale. L0q is negative 15.
Okay.
L1q is a 1 of 5.
Then it jumps to negative 455, then positive 1,365.
And then the really big boys showing up in the middle. Negative 3,003, positive 5,005, and negative 6,435.
It's important to notice the pattern there, even if you're just listening and not looking at the math. The numbers are oscillating, negative, positive, negative, and they are growing rapidly before shrinking back down.
It's like a bell curve of massive integers.
That's a good way to put it.
So normally, if I handed you this list of numbers and said solve for x, you'd panic. You'd reach for a supercomputer.
Right. Because calculating that by hand using traditional algebra seems impossible. It would take a lifetime. But Ezouidi's counterclaim is that we don't need to approximate. We can use a structured process.
Let's talk about that process, the machine. How does this theorem actually work? What is the mechanic here?
Visually, you should imagine a recursive loop. Recursive just means the output of step 1 becomes the input for step 2. It builds on itself.
Okay, so it feeds itself.
It does. The source outlines a specific formula involving a summation that's just adding up a series of numbers. And it uses those binomial coefficients you mentioned earlier.
The things that look like n choose k.
Exactly. It combines binomial coefficients, written as C with subscripts in the text, with the base coefficients we just listed, like the negative 15 and the 105.
So it's the grinder. You put in the raw numbers from the equation, turn the crank.
And it spits out a new number.
The new value, yeah.
It spits out a value called S sub KR. And here's the goal. We have to
is that if we calculate these S values, they will reveal the true structure of the equation.
Precisely. If the theorem holds, these calculated values won't just be random numbers. They will tell us something fundamental about the root. They peel back the layers of the polynomial to show what's hiding underneath.
All right, let's do the crunch. We're going to walk through these 15 steps, and I want you to listen closely because this is where the magic trick happens. It's a bit repetitive, but that's the point. It's relentless.
It's a machine doing its job. Let's start the engine. We begin at k equals 0. The text gives us a starting value. It's basically just initialization.
Easy enough. Now, k equals 1. We have a formula involving that first coefficient, negative 15.
We run the calculation. It involves a couple of terms. You get 225 minus 225.
And the result is?
0.
Okay, 0. That's a nice round number, maybe a coincidence. Let's move to k equals 2. Now things get a little harder.
Yeah, now we're squaring things.
We're taking negative 15 squared, and we're mixing it with that 105.
The calculation in the text shows terms interacting to balance perfectly. You have a negative number times a value plus another value. The math is getting dense, but when you sum them up.
Let me guess. 0. Again.
Again! Now moving to k equals 3, we're dealing with cubes. We have coefficients like -4, 55 coming into play. The numbers are getting larger. We have 15 cubed.
Which is, what, like 3,375? Big numbers.
Right. We multiply, we subtract, we have terms canceling out terms. Think of it like a scale balancing out. And the result for tie sub 3,
It's 0.
I think you're seeing the pattern forming.
I am. But let's push it. Because usually patterns break when the numbers get messy. Let's look at k equals 4. We have powers of 4. We introduce the coefficient 1,365. This should be messy.
The formula takes that 1,365, multiplies it by 15 to the power of 4, and subtracts a massive chunk derived from the previous steps. It's a huge calculation on paper.
Don't leave me hanging.
0.
Okay, this is getting spooky. It feels like we're watching a demolition derby where all the cars just vanish into thin air.
That's a good way to describe it.
Let's jump into the middle of the grind. K equals 5 through k equals 10. This is where the polynomial is heaviest. We have those massive thousands, 3,003, 5,005.
6,435. This is the battlefield. In step 6, for instance, you have 6,435 clashing with powers of 15 raised to the 6th degree. These are numbers in the millions.
The source text lists these long strings of calculations, like line after line of arithmetic warfare.
But notice what the recursive formula does. It's perfectly weighted. It uses those binomial coefficients, which are related to Pascal's triangle, to scale the numbers so they are exact opposites of each other.
So they're designed to cancel.
It's like matter meeting antimatter. So when you get to step 8, where you have that -5,005 coefficient, it interacts with the sum of all the previous terms.
Which have been carried forward.
And modified by the recursion, yes. They neutralize each other perfectly. The result is 0.
Step 9.
0.
Step 10.
It's still 0.
It's relentless. It's not an approximation. It's not 0.00000. It is exactly 0 every single time.
That's the distinction the source wants us to understand. A numerical method might leave you with residue, a little bit of leftover value because the computer couldn't handle the precision. This symbolic method wipes the slate clean.
So we're in the home stretch now. K equals 11 to k equals 14. The powers are astronomical now.
Numbers you wouldn't want to calculate by hand without this method. And yet, for k equals 12, the term involving -1,365 and 455 interacts with those high powers.
And the result is 0.
It remains 0. And finally, the big one, k equals 14. This calculation involves every single term that came before it. It's the final exam for the machine.
So it takes everything we've done so far and rolls it into one massive sum.
The source writes it out. You have the sum of all these massive oscillating products, and when you tally the final line,
It's 0. Of course it's 0.
S sub 14R equals 0.
So we have spent 14 steps doing massive algebra, and every single answer was 0. I have to ask the obvious question here. What does this actually mean? Have we just wasted our time proving that 0 equals 0?
Not at all. We've just performed a massive simplification. Think about what we have found. We found that all these intermediate coefficients, -0R, S1R, all the way to S14R are 0.
Okay.
Symbolically, the source explains that this transforms the polynomial, P of x. It effectively collapses the equation. It means that all those messy terms in the middle, the ones with the 3,003 and the 6,435,
They were just noise.
they were just noise created by the expansion. So instead of that long, scary string of 15 terms, it becomes something much, much simpler.
How simple.
The equation effectively becomes parenthesis x minus the root, close parenthesis, to the 15th power equals 0.
Wow. That is a lot cleaner. It's elegant. But we still need that root. We need to know what x is.
And this is the final reveal. The source text derives the root using the very first coefficient we started with, L0q.
The calculation is surprisingly simple after all that heavy lifting.
It is. We take L0q, which was -15. The formula says the root is determined by this value relative to the degree.
So we have -15. The degree is 15,
And the calculation is essentially -15 divided by 15.
which gives us -1.
Exactly. The root is -1.
-1. All those thousands, the 6,435s, the 3,003s, the millions involved in the powers. And the answer is just -1.
And not just any root. The source says it's a root of multiplicity 15.
Explain multiplicity for us again.
It means that the solution, -1, appears 15 times. The equation is actually just parenthesis x plus 1, close parenthesis, to the 15th power equals 0.
I see. So if you were to take x plus 1 and multiply it by itself 15 times.
If you sat there and did x plus 1 times x plus 1 times x plus 1 15 times, you would eventually generate that monstrosity we started with.
You would create the 3003s and the 5005.
You would. So Ezouidi's theorem worked backward from the monstrosity to find the simple kernel, -1.
That is incredibly satisfying. It's like untying a massive chaotic knot and realizing it was just one piece of string all along.
And it brings us back to the implications of this method. Let's reflect on that.
Yeah, because we started with Newton and Abel. We started with the idea that this was hard or impossible.
Right. Think about the difference in the experience here. If you used Newton's method on this, you would have gotten a number very close to medical 1. Maybe medical 1.00000003.
And you might have looked at that and said, it's probably medical 1.
You would have